Now, what velocity this represent in the prototype? So now the velocity in the model is given, and we have to calculate velocity in the prototype. The force exerted on a certain area of the model is measured to be 0.12 Newton. What would be the force on the corresponding area in the prototype? So now, as I told you before, that if you really know the scale ratios for these characteristics of physical quantities, then we can easily transfer the results between the model and the prototype. Now, in order to solve this problem, so you can see here that in this problem, it is not stated that for dynamic similarity, which is in addition to kinematic and geometric similarity, you consider which dimensionless number that we have just studied. You can see here we have to calculate the velocity in the prototype for the velocity which is given in the model. So you see that if you consider the Reynolds number, still we have the velocities. You can calculate the velocity from there. If we consider the Froude number, so then in that case, again, it links the velocity. So now you see the first step is to determine that what dimensionless number you have to consider. Now you can see here the flow problem which is given to us, that water flows over the crust of a spillway. So we know that this is actually open channel flow, and then in this case the Froude number, that will be important. You see this from your understanding it comes. It is not directly given in the problem that you consider the Froude number for dynamic similarity, and if the model velocity is this much, what will be the velocity in the prototype. So we first determine as a first step that gravity and inertia govern this flow. So Froude number criteria must be satisfied. Now in case of the Froude number, so we already studied that V divided by square root of GL, where L is the characteristic length. So this must be the same in both the model and the prototype. So this must be the same. Only then we can have the dynamic similarity between the model and the prototype. So this is M. Now G is the same for the model and the prototype. So that's why this G can cancel out if the model and the prototype, they are on different planets, or for example on the surface of a moon and another one on the surface of Earth, then in that case this G will vary. So now from here, if we ensure this, we define that the velocity scale ratio, that will be equal to Vp divided by Vm. And if you remember, for the case of Froude number, we already proved that this is equal to square root of Lr. You remember in the beginning of this lecture. And what is this Lr? This is actually the length scale ratio. Lp divided by Lm. And this can be written as power 1 by 2. Now this is given to us. So what is Lp by Lm? This is actually equal to 35. This is 35. So 35 divided by 1. So 35 we can write down, and this is power 1 by 2. So this is 5.92. 5.92. 5.92. Now it is asked to calculate the velocity in the prototype. Since we have the velocity scale ratio, we can easily calculate. So Vp, that will be equal to, you see from here, Vr into Vm. So this will be equal to Vm into Vr. So Vm is given, it is how much? It is 0.46 meter per second. Let me write down here 0.46 meter per second, and the velocity scale ratio that we have just calculated, that is 5.92. So what will be the velocity? 2.72 meter per second. This will be the velocity in the prototype. Clear? So this was actually part A of the question. So we calculated that this Vp, this is equal to 2.72 meter per second. Clear? Now in part B of the question, the force exerted on a certain area of the model is measured to be 0.12 Newton. What would be the force on the corresponding area in the prototype? So now we need to calculate the force scale ratio. If we can calculate the force scale ratio, then we can easily calculate the force in the prototype. So force scale ratio you need to develop. So how we can develop this force scale ratio Fr? This can be considered as the ratio of inertia forces, because inertia forces will be present in both model and prototype. So from there we can develop this. So this will be for the prototype and this will be for the model. So we already know the expressions for the inertia forces. So the inertia forces, that is rho v square L square, this is for the prototype, divided by rho v square L square, this is for the model. Now you can see here, this can be further written as rho into R, the density scale ratio, because it is prototyped by the model, into VR square, V is square, so it will be equal to VR square, and we have this LR, because it is LP by LM, so this can be written as LR square. Now if we are assuming that we have the same fluid in both the model and the prototype, so then this rho R will become equal to 1, because we have the same fluid in the model and the prototype. And this VR square, you see VR is equal to square root of LR. We have written that VR, that is equal to square root of LR. for Froude number similarity, now if you take the square, so VR square will be equal to LR. So that's why this VR square, this will be equal to LR. And then you have LR square. So this is actually equal to LR cube. So it means that the force scale ratio, that is equal to LR cube. Now you can ask a question that, okay, I consider the inertia forces in the model and the prototype, and the force scale ratio is equal to LR cube. If I consider the gravity forces, what will be the situation? So let us try to derive the scale ratio. If we consider the gravity forces, that what we get. For example, if I consider Fr, and that is equal to the gravity force Fg, that is in the prototype, divided by the gravity force that is in the model. So now what are the expression for the gravity forces? As we already studied in the previous lecture, that is equal to rho L cube into acceleration due to gravity. So this will be for the model, this one will be for the prototype, and we have the model also. Rho L cube into G, and this is for the model. Now this can be written as rho into R. We have L cube, so this will be LR cube, LP by LM, and we have GR, acceleration due to gravity scale ratio. Now you see that the fluid is the same, so rho R will be equal to 1. We have LR cube, and acceleration due to gravity is the same, so that will be equal to 1. So what we get, the force scale ratio from here, that is to be LR cube. So you can see here, if I consider the gravity forces or I consider the inertia forces, you see that the force scale ratio, that is equal to LR cube. So now the force exerted on a certain area of the model is this much. So the force in the model is given. So we already know that this Fr, that is equal to Fp divided by Fm. So now from here, we want to calculate the force in the prototype, that will be equal to Fm into Fr. So what is Fm? It is 0.12 Newton. So this is equal to 0.12 Newton. And we have the scale ratio that you need to calculate. So what is the scale ratio from here above? Fr, that is equal to LR cube. Clear? So this is 35 cube. So it means that this is 35 cube. Now from here you will get the force in the prototype. So that will be equal to 5145 Newton. So this is the answer. Now next we have this problem 7.13. it says that a 3 feet high sectional model of a spillway. So again, spillway, so means we have to consider the Froude number, is built in a 1 foot wide laboratory flume. The flow is 0.86 CFS under a head of 0.380 feet. If the model scale is this and the prototype spillway is 600 feet long, what flow does this represent in the prototype? So it means that we have to calculate the flow in the prototype QP. This is what we have to calculate. Now we already know that the flow on the spillway, the gravity forces and inertia forces that are significant. So that's why we have to consider the Reynolds number criteria. So then in that case, to solve this problem, we say that the Froude number, clear, in the model must be the same as the Froude number in the prototype. So this implies that we have this V divided by square root of GL. This is for the model. This must be the same in the prototype. Only then we can have dynamic similarity and we can transfer the results. So G into L, and this is for the prototype. Now you see, we want to calculate the discharge. So actually the discharge, that is equal to area into the velocity. This is the idea from here. So now it means that if I want to calculate the discharge scale ratio, because if I have the scale ratio, see, I can easily solve this problem. If I have the scale ratio for the discharge, this must be equal to the area scale ratio into the velocity scale ratio. Clear? Now in this case, what we see is that this velocity scale ratio, we already discussed, acceleration due to gravity is the same, model and the prototype both on the surface of the earth, so they are subjected to the same acceleration due to gravity. So this will be equal to LR power 1 by 2. And this will be equal to square root of, what is LR here? 20 by 1. So 20. So this will be equal to square root of 20. And this is equal to 4.47. This is the velocity scale ratio. Now your area AR, this is equal to LR square, LR into LR, so LR square. So this will be equal to 20 square, because LP by LM, so it is 20 by 1. So this is equal to, this is square, so this is equal to 400. Now discharge in the model, this is given as 0.86 CFS. You see that this 0.86 CFS, this is for a 1 foot wide laboratory flume. It means that this is actually discharge per unit width. So this is actually CFS per foot. Now the question is that we have to calculate the discharge for 600 feet long. So it means that, let's say we see the view of this spillway over which the water flows. This is 600 feet long. That we need to calculate. But in the lab, the width is 1 feet. This is 1 feet. Now you see the scale ratio, that is 20. Model scale is 1:20, or the scale ratio is 20:1. Now you see that we have to ensure 20, this scale here 20 to 1. It means that LP divided by LM. What is this? This is the scale ratio. Clear? This is 20 and this is 1. The model scale is 1/20. So we already discussed this. It should not create any problem for you. We will follow our textbook, LP by LM. Now in this case, is this 1 foot in the ratio, in this ratio? It is not. So that's why when we have to use this discharge ratio, which we will calculate here, the discharge scale ratio, AR into VR, that is for 20. The length scale ratio is 20. So that's why what we need to do is that we should convert this discharge in the model. This will be equal to 600 by 20. 600 divided by 20. Clear? So from here, what is the answer? This is equal to 25.8. This is now 25.8 CFS, and this is now following this scale ratio. Clear? And now what we can do here is that this QR, this will be equal to QP prototype divided by the model. Now this QR is for this scale ratio. We calculate or convert the model discharge for that ratio. So now from here, we can say that QP, that is equal to QM into QR. So now from here, this comes out to be, what is QR from here? AR into VR. What is AR? 400. What is VR? 4.42. So this QR, which is equal to AR into VR, this is equal to, what is AR? 400. So this is 400. What is VR? 4.47. So now this QR, this comes out to be 1788. It is a ratio, no units. So now this QM, which is 25.8, and QR, which is 17.88, so this is equal to 46,130 CFS. This is the answer. So you can see here that the scale ratios, actually how much they are helpful in analyzing the problems. Clear? That's why the full table that is given in your textbook to highlight its importance. Now the next problem is problem 7.26. Now in this case we have a gas whose density and kinematic viscosity are given, and it is flowing in a 20 millimeter diameter pipe. When a gas flow meter measures the flow is being this much, this is now the mass flow rate. You see the flow is 0.064 kilogram per second. So this is the mass flow rate. Clear? That is actually denoted in your textbook by m dot. So this is actually equal to rho times q, mass flow rate. So this is in kilogram per second. What we commonly use, that is the volume flow rate. So that is in cubic meter per second. So when we are dealing with the incompressible fluid, as we commonly study in our case, water, the water is considered as incompressible for practical purposes. That's why it is, you see that commonly we are using volumetric flow rate. But when we deal with compressible fluids, so in compressible fluids, it is more convenient to deal with the mass flow rate and the weight flow rate, if I'm correct. So it is G dot, that is equal to weight flow rate. Let me just avoid this writing here. The weight flow rate, that is the Newton per second. Clear? Let me write down here. If this is the weight flow rate, you can use the correct notation. If this is not correct, that is in Newton per second, weight flow rate. When we deal with compressible fluids, then in that case the mass flow rate, the weight flow rate, these become convenient to work with. But so far we have not used them because we are dealing with incompressible fluid problems most of the time. So you can see here the flow here is given as the mass flow rate. Clear? It registers a pressure drop of 8.5 kPa, kilopascal, kilonewton per square meter. Now investigators plan to test an enlarged model now. You can see in an example here, we are using the model that is bigger than the prototype. That is geometrically similar in a 180 millimeter diameter pipe. The first part of the question is what flow rate of 25 C water, centigrade water, will achieve dynamic similarity. And the second part of the question is what would be the pressure drop across the water meter. So now what we have to do is that in this case the model is enlarged, and in the model we are using water, whereas in the prototype we have the gas. So it means that now the fluid properties will be different. So let us try to solve this problem step by step. So now in part A of the question, we have to determine that what flow rate of 25 C water, that is the discharge in the model, that will achieve dynamic similarity when the discharge in the prototype, that is in the mass flow rate, that is given 0.064 kilogram per second. Clear? So now in this case we have the pipe flow. So now in this case we have to determine that inertia and friction due to viscosity, because you see the viscosity is given above. Inertia and friction due to viscosity dominate the pipe flow, so it must satisfy the Reynolds number. So now when you solve this problem, you see that we have to satisfy the Reynolds number criteria. This criteria we have to satisfy. If you use other than the Reynolds number, you see the results will not be accurate. So for the Reynolds number, we have to calculate the discharge. So first you have to develop the scale ratio for the discharge. First you have to develop the scale ratio for the discharge considering the Reynolds number similarity. So that's why you see the table which is given in your textbook, that can be helpful. If I go back, you see that the table that we just discussed, this was the table which is given in your textbook here. And you see for the Reynolds number, this is the Reynolds number. Where is the discharge? This is the discharge. This is the discharge. And this is the Reynolds number. So this is the scale ratio. This scale ratio you can directly use in the problem. This is already developed. So you can see the importance of this table. It can help, these scale ratios can help in the solution of the problems. So this scale ratio for the discharge, the Reynolds number, if you want to satisfy this, you have to use. So let us use this when we solve the problems. So here what was the scale ratio? That this QR, that will be equal to L into mu divided by rho, and this is whole with a subscript R. It means that this for the prototype divided by this for the model. Remember, whenever R is written in the subscript, so it means that it is the scale ratio. And this can also be written because kinematic viscosity is given, so this can also be written as LR into nu R. This is now not velocity, kinematic viscosity, because mu divided by rho, that is your kinematic viscosity of the fluid. So now if I can calculate this QR, I can multiply this with this prototype, not multiply in this case, but this prototype discharge divided by this scale ratio, this will give us the discharge in the model. And in this case we have enlarged model. Clear? So actually what we have this QR, this is equal to QP divided by QM. So now QM we have to calculate. So QP is given. If I can calculate QR, that I will divide QP divided by QR will give us QM. This is what is part A of the question. So let us calculate the value of this QR. Now you see here that we have the ratio, scale ratio for the kinematic viscosity. So now the kinematic viscosity for the prototype is given, which uses gas. We need the kinematic viscosity for the model fluid, which is water. So at 25 degree centigrade water viscosity, that you can read from the table. Now LR you can calculate because the diameter is given in the prototype and the diameter is given in the model. So we can easily first calculate LR. LR will be equal to LP divided by LM, length scale ratio. So LP is 20 in the prototype, the model is enlarged, so it is 180. So the length scale ratio is 0.11. This is the length scale ratio, 0.1111. Now to calculate the scale ratio for the viscosity, Only then we can calculate the discharge scale ratio. So you need the value from the table. You see, for 25 degrees C for water, we have table A.1 in the appendix, end of the book, table A1. So at 25 degrees C for water, kinematic viscosity, because water is in the model, so kinematic viscosity is 0.893 into 10 power minus 6 square meter per second, and the density also, if we need, for water at 25 degrees C, that is 997 kilogram per cubic meter. Now you can easily calculate the scale ratio for the kinematic viscosity. So this VR, this will be equal to kinematic viscosity in the prototype divided by kinematic viscosity in the model. So you can plug in the values. So this comes out to be 22.4. This is 22.4. Now what we have to do is that QR, the discharge scale ratio, that is equal to this LR into nu R. This is equal to LR into nu R. So what is LR? 0.1111 multiplied by 22.4. So you will get the discharge scale ratio. So this is the discharge scale ratio, 2.49. Now we want to calculate the flow rate for water. So as I said, for incompressible fluid, it is convenient to work with volumetric flow rate, but the flow rate for the gas, which is compressible fluid, it is given as mass flow rate. So for the prototype, we can calculate the volumetric flow rate. How to do it? This will be equal to this m dot divided by rho. Clear? So what is m dot? You see, m dot is rho q. This is the mass flow rate. This is rho q. So divided by rho, it will become q, which will be volumetric flow rate. So this will be equal to 0.01219 now cubic meter per second. And now what will be Qm? Qm will be equal to, from here, Qm will be equal to Qp divided by Qr. So this is equal to 0.0049 cubic meter per second. This will be the discharge in the model. What flow rate of 25 degrees C water will achieve dynamic similarity? So this will be the discharge. Now next we have part B of the question. So now in this case, it says that what would the pressure drop across the water meter be? So now in this case, we need the pressure scale ratio. So again from the table, you will come here again in the table and we have this pressure here, and for the Reynolds number, this is the pressure scale ratio. This is for the Reynolds number. So this you will pick from here. So now for the Reynolds number, we have this PR, the pressure scale ratio, that will be equal to mu square divided by L square into rho, and this is R, means that it is the ratio. This for the prototype divided by the model. And this can also be written as rho into nu square. Just you adjust, this will be equal to L square into R. So now you can easily calculate. You see we have the density for the prototype, we have the density and everything for the model. So you can easily calculate, just put the values here, everything is known. You put the values, this comes out to be 214. Now, what would be the pressure drop? So let us assume this, that the delta PR, the pressure drop ratio, that is equal to the drop in pressure in the prototype divided by the drop in pressure in the model. This is equal to 214. Now, delta PM we have to calculate. This is what is asked. What would be the pressure drop across the water meter? So that is in the model. So delta PM, that will be equal to delta PP for the prototype. This is 8.5 kappa. For the prototype it is given. And this divided by this delta PR, the pressure scale ratio. So this will be equal to 8.5 kappa divided by the scale ratio, which is 214. So now this delta P, change in pressure for the model, this will be equal to 0.0397. So this is kappa, kilopascals, or this can be written as 39.7 pascals. So this is Newton per square meter. Clear? So this is how we solve these problems. Clear? Now the next parallel topic to this is the dimension analysis. So we study some introduction, then we will continue this discussion in the next class. This dimension analysis, what is this? The learning objectives for this topic. After completing this topic, you should be able to develop a better understanding of dimensions, units, and dimensional homogeneity of equations. So this dimension analysis topic, which is second part of this chapter, The first thing is you will understand about the dimension. You see dimensional analysis. It means we have to deal with the dimensions of the physical quantities in any fluid mechanics, fluid flow phenomena. And what we mean by dimensional homogeneity of equation, it means that all the terms, they have the same units. For example, you consider the Bernoulli equation. So when we have the velocity head, the datum head, elevation head, the velocity head, and the pressure head, same units. So it is dimensionally homogeneous. This we have to understand what we mean by dimensional homogeneity, what are its advantages. The second thing is to understand numerous benefits of dimension analysis. Why we need to study this topic? What could be the possible advantages, benefits of this dimensional analysis? And the third one is to know how to use the method of repeating variables to identify non-dimensional parameters. So in dimensional analysis, we will use different methods. One of the method is the repeating variables, which is very important method, and that is actually the pi theorem. So we will use this method, we will know how to use this method, and then in the problem, how we can identify these non-dimensional parameters if present. For example, the Reynolds number, the Froude number, the other dimensionless numbers that I told you, and there are many number of dimensionless numbers. Clear? In fluid mechanics, many, as I told you, more than 150 are mentioned in the Handbook of Fluid Dynamics by Johnson. So how you will identify this? This is what we are going to learn. And then what will be the advantage of this? Because you see this non-dimensional parameter that we can identify, we are actually using them in similitude, and they help us to transfer the results between the model and the prototype. So you can see that by end of this topic, you should be able to achieve all these objectives. So let us start with this dimension analysis. Let me further highlight the importance of study of this topic. Why we need to study this topic? So we consider the flow of fluid in a pipe. So in this case, you see that we are interested to develop an expression for the drop in pressure, change in pressure, which will be equal to, this is per unit length, so divided by L. So you have pressure at one point and pressure at the second point, change in pressure. So divided by L, it is the change in pressure per unit length. So now we want to develop a functional relationship for this change in pressure. So first what you have to do is that you have to identify that what parameters you need to consider that can affect, clear, this change in pressure that occurs. That's why I told you that in similitude or in this dimension analysis, a basic understanding of the fluid phenomena is very important. For example, in this case, we know from our basic understanding that this change in pressure, it is a function of the diameter of the pipe, the density of the fluid, the viscosity of the fluid, and the velocity of the flow of that fluid. So this comes from the basic understanding of the phenomena. If, for example, you do not have the good understanding and you omit any parameter, or you bring additional parameters which are not significant, then you can see that it will be very difficult to analyze the situation. That's why I say again, and I repeat it here, that for model studies and for this dimension analysis, one must have basic understanding of the fluid phenomena. This is step number one. And then we can proceed and we can get some meaningful results. So now from our basic understanding, we determine that, okay, this change in pressure is a function of these four parameters. So these are the independent parameters and this is the dependent parameter. Now we want to establish a functional relationship between this. Now one way is that you derive the formula, use some mathematical technique, you develop and you derive the formula. Well, let us assume that in this case the theory is not sufficient to give insight and we can develop the formula. So what is the alternative? So the alternative is you do experimental work. And now how to conduct the experiment? If there is one independent variable, one dependent variable, it's very easy to conduct experiment. You just change the parameter, calculate the other parameter, and then plot a graph or do the regression analysis. You can easily develop a functional relationship. But now as the parameters increase, it becomes very difficult. But now we want to do experimental work. So how we can systematically carry out the work? So what we will do is that first we consider this dependent variable and one independent variable at a time. So if you change the values of V, what is the effect on the change in pressure, keeping the other as constant? This is how systematically you have to move. So now let us assume that you need minimum 5 points to plot a graph for this delta P. You can say 10 points, 20 points, no problem. Let us assume that you need minimum 5 points to plot a graph. So now it means that you have to vary this V by keeping these values as constant, clear? Then in the next stage, what you will do is that you keep these variables as constant and you consider the effect of change in diameter on this delta P. Then in the third stage, you keep these parameters as constant and you check the effect of the density versus the change in pressure. And you consider the effect of viscosity on the change in pressure by keeping these as constants. And you see the difficulty is that if you keep density as constant, how you will vary the viscosity? So now you can see here that we have 4 independent variables, and if you need minimum 5 readings for each, so we have 5 and then 5 and then 5 readings and then 5 readings for one setup. This is for one constant value of these parameters. If you want to test for full matrix of that, if you want to get these 5 values for full matrix, full range, then it will be 5 into 5, 5 into 5, and 5 into 5 means that actually this will be 5 power 4. It means that this much, this is how much? 625. If I am correct, this is 625. So it means that you have to conduct 625 experiments to get a functional relationship for these variables. And then 625 experiments, you do it, and you see the facilities need to be available and the time it takes to conduct 625 experiments, the efforts, because you need expert to be yourself or somebody else to do the job for you. And if one experiment is costing, let's say $1, 10 rupees, whatever, then the amount of money you need to conduct these experiments. This is if you need 5 readings. Let's say somebody tells you that no, I need 10 readings minimum for plotting this delta P. So then in that case you see 10 by 10 by 10, 4 parameters, so you need 10 to conduct 10,000 experiments. You need to conduct 10,000 experiments. and you see the time it takes, the effort it takes, and the money it takes. Now what we do is that if I can apply the dimensional analysis, these 4 parameters I reduce to just one parameter, that is the independent parameter here. Here dependent, this is the independent dimensionless group or product. Here you see no units here, no units here. So now in this case what we have? We have one independent variable and one is the dependent variable. So if I plot a graph, so now you need minimum 5 points, and now we reduce the 4 parameters to just one parameter. So 5 times 1, it means you only need to conduct 5 experiments to get the functional relationship. In this case, if you consider here and you consider another variable here, this one, so you only need to conduct 5 experiments to get the same relationship as you need to conduct 625 experiments to get the same result. You will conduct 625 results if you need 5 minimum points, or if you say I need 10 points, then you need to conduct 10,000 experiments. You will get a functional relationship between the two. Here, these variables, dependent and independent. And if I can use these parameters, this one and this one, I only need to conduct 5 experiments to get the same result. How much effort is reduced? How much experiments are reduced? How much money is saved? And this is only possible by this dimension analysis. So you can see the importance of dimension analysis. It helps us, you see, in the design of experiments. It helps us to establish a functional relationship with minimum effort. Of course, you see the idea here is that we reduce the number of parameters from 5 to just 2 parameters, dimensionless groups, dimensionless products. This is what we actually do in dimension analysis. So how we do it, that is another story. We have different methods to do it, but this is the importance of this topic that we need to study. And you see the other advantage is that when we apply the dimension analysis and we get this functional relationship, we reduce the number of parameters to minimum possible. We identify that this rho Vd by mu is familiar, something familiar. And we find out that this is actually Reynolds number. This is actually Reynolds number. So it means that this dimension analysis, you see, it gives us insight into the problem. That this change in pressure, the functional relationship that we establish, is actually a function of a Reynolds number, which is a dimensionless number we just studied in the similitude. So in other words, you see in the problem, you have to struggle that you want to solve this problem here. You are struggling that which number is important to be considered. When we deal with the variables using dimension analysis, it can tell you that which parameter dimensionless number is important. So in other words, this dimension analysis actually provides the basis for similitude, the laws of similitude. because you see this law of similitude based on the Reynolds number what we use to solve the problem. So this is actually the importance of dimension analysis. You can see that how much this is important topic. So I will just highlight the importance, then I will stop it here. We will continue with this discussion in the next class. Let me just finish with this slide. You see, one of the most useful applications of dimension analysis is in designing physical and or numerical experiments and in reporting the results. Setup of an experiment and correlation of data. This is what I show you in the previous slide. This is what I already explained to you. That if we consider a problem with 5 parameters, 1 dependent and 4 independent, the full test matrix with 5 data points, if you need to conduct 625 experiments. But with the dimension analysis, we can reduce the 5 parameter to just 2 dimensionless groups, which we will call it as pi. So the method is Buckingham pi method. I will later on explain in the next class why it is called a pi group. So we reduce the 5 to 2 dimensionless parameters. So that's why you need only 5 experiments to get the result. This is possible due to this dimension analysis. And also it can tell you the trend between the parameter. You see direct relationship or non-linear relationship, whatever. So in most experiments, to save time and money, tests are performed on a geometrically scaled model, not on the full-scale prototype. This is what we have studied so far. So in such cases, care must be taken to properly scale the results. Thus, powerful technique called dimension analysis is needed. The 3 primary purposes of dimension analysis are to generate non-dimensional parameters that help in the design of experiments and in reporting of experimental results. This is what you see here. That using the dimension analysis, we come up with that for this specific case, the Reynolds number is important. We didn't know before. We did the analysis and we come up that, okay, this is familiar thing. Wait a minute, this is Reynolds number. In other problems, maybe we come up with other dimensionless number that are important, like the Froude number, the other number we studied. It's not that always we get Reynolds number. It will depend on the flow problem. So you see the dimensional analysis, it helps us to determine this non-dimensionless numbers. To generate non-dimensional parameters that help in the design of experiments and in reporting of experiment results. To obtain scaling laws, you see the laws of similitude, because it tells us that this is the dimensionless number. So for that dimensionless number, we obtain the laws of similitude so that the prototype performance can be predicted from the model performance. And to predict trends in the relationship between the parameters. You see here that you have linear relationship, you have non-linear relationship, you have direct relationship, you have indirect relationship. So you can see here that this dimension analysis is very powerful tool. This is very powerful tool. Clear? So we will continue with this dimension analysis. I just come up to here and then from here we will continue in the next class. So dimension analysis is a mathematical technique making use of study of dimensions. So it is just a mathematical technique. We play with the dimensions of the physical quantities and we analyze the problem. We have different methods to do it. It deals with the dimensions of the physical quantities involved in phenomena. In dimension analysis, one first predicts the physical parameters that will influence the flow and then by grouping these into these dimensionless combinations, a better understanding of the flow phenomena is made possible. As I told you, you see what is the first step. One first predicts the physical parameters that will influence the flow. So now, if you miss out important parameters or you bring in unimportant parameters into the analysis, then you can see that the effort will be more, the solution will be difficult to analyze, and you will not get realistic results. That's why I repeat that in similitude and in this dimension analysis, a basic understanding is must. Because if you pick the wrong parameters, then you will not get the required results. So this is important. It is particularly helpful in experimental work, as I already explained, because it provides a guide to those things that significantly influence the phenomenon. Thus, it indicates the direction in which the experimental work should go. For example, you see how much effort is reduced because of this dimension analysis. That's why this is used in the design of experiments, not only in civil engineering, maybe in chemical engineering, in chemistry, in physics, and other branches of engineering where we need to conduct experiment and research work. You can use this dimension analysis for guidance. So this mathematical technique is used in research work for design and for conducting model tests. So you can see here that how important this topic is. So in the next class, then we will continue how we apply the methods to do this dimension analysis, and the objectives that I mentioned, you should be able to achieve those learning objectives